Welcome, everyone, to today's session on architecting AKS networking. As organizations increasingly rely on Azure Kubernetes Service for their mission-critical applications, the underlying network design becomes a fundamental pillar of success. Today, we are going to walk through a comprehensive blueprint for building a robust infrastructure. We will cover the technical nuances of subnet sizing to ensure you never run out of address space, compare different CNI models to find the right balance between performance and simplicity, and establish a clear scaling strategy that allows your clusters to grow seamlessly with your business needs. Let's dive into how we can design a network that is both resilient and highly scalable. When designing Azure virtual networks, it is essential to understand the specific constraints of subnet sizing. The core rule for determining capacity is defined by the formula usable IPs equal 2 to the power of 32 minus the CIDR prefix minus 5. Unlike traditional networking environments that typically subtract only 2 addresses, Azure reserves a total of 5 IP addresses within every subnet, regardless of its overall size. As shown in the diagram, these 5 addresses are essentially removed from the usable pool and reserved for internal platform management. These include the standard network and broadcast addresses, along with 3 additional IPs dedicated to infrastructure services, the default gateway, and the addresses used for Azure DNS mapping. When performing capacity planning for your cloud infrastructure, always account for this subtraction to ensure you have enough usable addresses to accommodate your virtual machines and service endpoints. This subnet sizing cheat sheet provides a quick reference for calculating IP address availability within Azure environments. You will notice that for each CIDR block listed, the usable IP count is derived by subtracting 5 from the total. This is because Azure reserves 5 specific IP addresses within every subnet for internal management and routing purposes. Moving through the scale, a /16 prefix provides over 65,000 usable addresses, while a standard /24 subnet offers 251. The range from /22 down to /27 is highlighted as the AKS zone. This range represents the most common subnet sizes for Azure Kubernetes Service deployments, as it provides sufficient headroom for nodes, pods, and service scaling. At the smaller end of the spectrum, a /29 subnet yields only 3 usable addresses. Finally, it is critical to note that a /30 subnet is not usable for standard Azure resources, as the 5 reserved addresses exceed the 4 total addresses available in that block. When designing your network architecture for Azure Kubernetes Service, it is essential to understand the 3 primary pillars of IP consumption. The first pillar is the node subnet. This is a mandatory component where every node in the cluster consumes 1 IP address from the designated subnet for its own operation. The second pillar is the pod subnet. In a non-overlay Azure CNI configuration, pods pull their IP addresses directly from the VNet. It is vital to plan for pod density, as the default maximum number of pods per node is 30 for standard configurations or 110 when using Azure CNI. The third pillar is the service CIDR. This range remains independent of the VNet and is used exclusively for internal service load balancing. Because it is independent, it does not consume any IPs from your Azure subnets, providing a scalable solution for internal communication without depleting your VNet resources. This slide examines the architectural mechanics of non-overlay versus overlay networking. On the left, the non-overlay model treats pods as first-class VNet citizens. In this configuration, each pod receives an IP address directly from the VNet range. This approach requires the node to reserve 1 IP for itself, plus an additional IP for every possible pod, or 1 plus max pods. While this ensures direct visibility and simplified routing, it requires a substantial allocation of VNet address space. Conversely, the overlay model on the right is designed for IP efficiency. The node uses exactly 1 VNet IP address, regardless of how many pods it hosts. The pods reside in a private, disconnected overlay space and are assigned IPs from an internal network that is separate from the VNet. This architecture allows for significant cluster scaling without exhausting the primary VNet's available IP resources. To understand the practical impact of these configurations, let's examine a scale comparison where both scenarios deploy 10 nodes with 30 pods each. On the left, we have a standard deployment within a /22 subnet. In this model, every node and every individual pod requires a dedicated IP address from the subnet pool. This results in 310 IPs needed, creating significant pressure on the subnet and limiting overall scalability within the virtual network. On the right, we see the efficiency of an optimized networking approach. Here, only the nodes require IPs from the primary subnet, reducing the total requirement to just 10 IPs for the same workload. This allows for the use of a much smaller /27 subnet while still leaving room for growth. This comparison demonstrates a massive reduction in VNet IP usage, enabling far greater scale with a significantly smaller IP footprint. The reality of CNI overlay is a story of trade-offs, often visualized as a balance between scalability and management overhead. On one side, overlay networking provides a massive win for addressing subnet pressure and enabling seamless multi-cluster scaling. It allows organizations to bypass the limitations of physical infrastructure to reach a truly massive scale. However, this is not a free lunch. As the scale on the right indicates, these benefits are directly balanced by increased operational complexity. Designing and maintaining an environment with CNI overlay requires a willingness to accept fundamental shifts in networking physics, governance, and observability. To succeed, teams must move beyond traditional networking mindsets and prepare for the unique challenges that come with an abstracted network layer. Let's examine the trade-offs associated with using an overlay network, specifically focusing on physical performance and operational complexity. At the top of the diagram, we see the VXLAN shell. When a data packet is encapsulated, it adds overhead, which results in what we call MTU shrinkage. Because the VXLAN header consumes space within the standard frame, the effective maximum transmission unit for the actual payload is reduced. Looking at physical performance, the primary concern is encapsulation overhead. Since every pod-to-pod packet carries these extra VXLAN bytes, network efficiency is impacted. Additionally, there are throughput limits to consider. The requirement for extra processing hops and a potential lack of hardware-level VXLAN offloading on the node's NIC can lead to lower maximum throughput, which is a critical consideration for high bandwidth or machine learning workloads. Shifting to operational complexity, an overlay architecture introduces more moving parts into the environment. This includes the Cilium data plane, the VXLAN tunnels themselves, and additional control plane components that must be maintained. Finally, this creates a more complex packet path. Because packets require constant translation between the overlay space and the underlying virtual network, troubleshooting becomes significantly less intuitive and more time-consuming for operations teams. When implementing an overlay network, we must carefully consider the trade-offs regarding security and observability. One of the primary challenges is what we call the NSG blind spot. Because network security groups only see node IPs rather than individual pod IPs, pod-level security enforcement can no longer be handled at the infrastructure level and must instead shift to a tool like Cilium. Furthermore, we encounter routing constraints, where pod IPs are strictly non-routable outside of the cluster. This creates a state of on-prem isolation, meaning legacy systems that expect direct pod access will fail to connect. On the observability front, there are significant gaps to bridge. Standard network tooling, including TCP dump, VNet flow analytics, and CM correlation engines, often assume that pod IPs reside directly on the VNet. To maintain effective monitoring, these tools require adjustments to map pod traffic back to the host node. Consequently, existing dashboards and operational runbooks must be updated to account for this lack of native pod visibility on the underlying network. Let's examine the strategic trade-offs between overlay and non-overlay networking models to determine which architecture best fits your specific requirements. You should generally avoid an overlay model if your pod IPs must be directly routable from on-premises networks, or if your security posture mandates a strict reliance on NSG-based pod segmentation. It is also the less favorable choice when your applications require ultra-low latency or massive east-west bandwidth. Finally, for teams that prioritize the simplest possible troubleshooting path for packet tracing, a non-overlay approach remains the preferred option. Conversely, an overlay model is ideal when designing for massive cluster scale without the risk of VNet exhaustion. It allows you to drastically simplify your subnet planning and helps in reducing overall VNet fragmentation. Furthermore, when building multi-cluster architectures that require consistent IPAM across various environments, the overlay model provides the abstraction necessary to scale efficiently and predictably.
The diagnostic matrix provides a direct comparison between non-overlay and overlay networking models across 5 critical dimensions. Starting with subnet pressure, a non-overlay approach creates high demand on your address space because every pod consumes a VNet IP. In contrast, an overlay model maintains low pressure, making it the ideal choice for large-scale deployments. Regarding on-prem routability, non-overlay allows for direct routing to pods, whereas an overlay model restricts visibility to node IPs only. From a governance perspective, non-overlay is often preferred because Azure Network Security Groups can see pod IPs natively. In an overlay setup, security relies on tools like Cilium operating inside the overlay itself. In terms of performance, the non-overlay model provides a simpler path with zero overhead. Conversely, the overlay model introduces VXLAN overhead, which can limit your maximum throughput. Finally, for observability, native VNet tools work instantly with non-overlay configurations. Using an overlay model requires additional pod-to-node mapping within your CM to achieve the same level of diagnostic clarity. These trade-offs highlight that while overlay excels at scale, non-overlay offers superior performance and integration with native cloud tools.
Architectural synthesis requires us to navigate the tension between traditional governance and cloud-native modernization. On the left, the traditional governance focus is defined by an NSG-heavy, VNet-centric audit profile, often driven by legacy integration needs. The strategic direction in this path is to maintain a non-overlay network architecture. This ensures direct pod IP visibility within standard network security groups and flow logs, which remains a critical requirement for many established compliance frameworks. In contrast, the cloud-native modernization profile prioritizes service-centric access, utilizing gateways, zero-trust frameworks, and identity-based security. This approach favors the adoption of overlay networking, shifting enforcement higher up the technology stack. By moving in this direction, organizations can leverage advanced tools such as Cilium for eBPF-based security, OPA and Gatekeeper for policy management, and service meshes to ensure robust MTLS throughout the environment. The decision between these two paths ultimately depends on whether an organization prioritizes traditional infrastructure visibility or a modern service-abstracted security model. When deciding between non-overlay and overlay networking, this shortcut helps clarify the most critical architectural requirements. Choose a non-overlay configuration if your environment requires partner networks to route traffic directly to pod identities. This is also the necessary path if your security policies strictly mandate that pod traffic remains visible to network security groups for granular filtering or auditing. Furthermore, because non-overlay networking avoids the encapsulation overhead, it is the optimal choice for workloads that are highly latency sensitive. Conversely, you should choose an overlay network if you are actively facing VNet IP address exhaustion, as it allows pods to operate in a private, non-routable address space. This model is particularly effective when deploying a large fleet of multi-region or multi-team clusters, where IP management can become a significant bottleneck. This approach works best for teams comfortable utilizing Cilium as their primary network guardrail, and for environments where access patterns are identity first, rather than dependent on specific IP addresses. There are 3 key takeaways to keep in mind regarding network architecture. First, precision in your math is non-negotiable. You must always account for the 5 reserved IP addresses per subnet before you calculate node capacity to ensure your subnets are sized correctly. Second, understand the trade-offs inherent in your networking model. While an overlay network solves for scale, it shifts complexity. It trades IP pressure for encapsulation overhead and more opaque VNet visibility. Finally, let your strategy and governance dictate the path forward. Your requirements for security, routing, and observability should drive your CNI choice just as much as your IP limits do. Focusing on these priorities ensures your network is built for long-term scalability and operational success.